Welcome. One of the things I still don't know how to do is in the discrete to have a natural notion of sectional curvature, which gives you all the notions you want to have, like positive curvature manifolds should be spheres if sufficiently pinched. There should be the common list of known positive curvature manifolds, theorems which we know in the continuum should hold, or conjectures which we know in the continuum should hold. Positive curvature manifolds, for example, should have positive Euler characteristic, and it should not just be a numerical scheme like averaging over long range. The problem is in the discrete we don't have a notion of plane, natural notion of plane. So I experimented with a half a dozen of different notions. One of the things you can do is take 2 points, let waves work, and then or 3 points in 4 dimensions, and look at the level surfaces and consider them to be planes, and then look at the curvature of these planes, the usual curvature which we have, this curvature of which Eberhard already had in 2-dimensional surfaces have already very nice curvature living on vertices. But what I want to do here is having curvatures live on edges, kind of like a Ricci type, or curvature living on faces, which maybe is something good for sectional curvature notions. But this is still unexplored, and it should satisfy the Gauss-Bonnet. Curvature which doesn't satisfy Gauss-Bonnet, I just am not interested in. The whole setup is here, kind of the little bit large scale picture. So this all works in a delta set, which is a kind of a just getting to the G's. We really want to have a finite set, and we want to have a Dirac operator. The Dirac operator gives us the geometry, gives us the homology, and R, the dimension, is necessary in general also to add. And then we have a Hilbert space, which is all functions which we have there. These are differential forms, and we can look at this index in the context of Atiyah-Singer. That's kind of the fancy way to look at that. We look at this Euler-Poincaré formula as index formula. So the index, the dimension of the kernel of D minus the dimension of the kernel of D star, that's the index. So there is a little bit a catch here. So D can be seen not only as a map on the Hilbert space itself, but as a map from the even dimensional part of the Hilbert space to the odd dimensional part, going forth and back between this fermionic or bosonic part. And then we have this, we look at these differences, which is nothing else than the number of positive, the number of even BKs, Betti numbers, minus the number of odd Betti numbers. So it's the dimension of the harmonic forms which are even dimensional minus the dimension of the harmonic forms which are odd dimensional. That's just a fancy way to say this. And then there's a second part which relates this with local quantities, which is the Gauss-Bonnet part. Also, this can be formulated in a more fancy way by talking about topological index, but it's maybe better just to think about it as curvature. It's something locally defined, and there are many ways to do that. So already the Wx, the -1 to the dimension of x, is already a very good curvature, right? You add up all these curvatures. That's the definition of Euler characteristic or whatever characteristic you are looking at. I'm also looking at quadratic characteristic, cubic characteristic, any higher characteristic. This is all in this framework. And then there's this McKean-Singer symmetry, which is absolutely central. McKean-Singer allows you, for example, then to shove everything or project everything down to the harmonic forms using the heat flow. That gives you then this index here. A consequence of this McKean-Singer is that you can take rather arbitrary curvatures here, which are just diagonal entries of wave operator. So like cosine dt, for example, is solution of the wave equation. So you can look at that, and then you look at the diagonal elements, and so the supertrace stays the same. So when we take Wx times that adds up to essentially just directly following from McKean-Singer. Another thing I'm interested in is green functions. If you take the green functions in the connection calculus, also there you can add up all the supertrace of all the diagonal elements of the green function, also gives you the Euler characteristic. That's this energy formula which I proved in 2016. So it's all related to invariance, topological invariance. And this part kind of shows this is stable, right? This is something which doesn't change under perturbations because it's integer. Like integers don't change under topological changes. While the other thing, this is not obvious. It comes always with three different ways. You can either look at it as Gauss-Bonnet, or you can look at it as Poincaré-Hopf if the energies of the simplices are going to the vertices, the zero-dimensional part, in a deterministic way, given by a function. But then you can also average this. If you have an average of all functions, an average probability measure on a Hilbert space, that gives you then a curvature. Of course, what happens is when you shove everything from the simplices to the zero-dimensional part, nothing gets lost. So that's kind of that's the second part of the Atiyah Singer, the book of ballet, for example. Or so it's very complicated. There's a lot of technicalities. It's a little bit like reading Goethe, and some of my friends who at high school were, instead when we were reading Goethe, like Die Leiden des jungen Werther, were reading Bukowski. This is somehow like a poem of Bukowski, you know, very provocative to look at it this elementary way. This is just linear algebra. It's something we can do very early on. Now, today is something also quite nice, I think, because it can be applied to polyhedra, for example, or any graph. You can, instead of pushing the curvature down to the zero-dimensional part, which we usually do, like here, the Leavitt curvature, which is gives this Eberhard curvature, which is Birkhoff was using this in the graph coloring situations, and so you add up all these curvatures, you get Euler characteristic. For example, here the degree is 5, so 1 minus 5 over 6, that's 1/6. So the curvature which you attach here to every vertex is 1 over 6, and you have 12 vertices in this icosahedron. Total Euler characteristic is 2. So that's also already Atiyah Singer. So it's somehow in the spirit already of Atiyah Singer. And then you can express it using cohomology, right? So there is only the zero-dimensional cohomology and the two-dimensional cohomology are 1. And so this gives us also 2. So I wonder, just in the context of when you want to look at Ricci curvature or something, Ricci curvature is just the average over all sectional curvatures over an edge. So you can look at Ricci curvature as something which is attached to edges, and sectional curvatures you can think about something attached to geodesic surfaces. Take a point, let the dimensional plane, and let the geodesic flow move, and then you look at the curvature in that direction. That gives you then also the Riemann curvature tensor you can get like this if you know all sectional curvatures. So somehow this is an attempt to get into that. This is quite nice. I mean, what we do is, in here, what we did, we pushed everything to the zero-dimensional part. So we leave the zero-dimensional part. That's the vertex energy. Then we take the edge energy, which is kind of, how many do we have? We have 5 edges, which contribute by 1/2 because they share 2 vertices. And then we take all triangles, which are also 5. And then these triangles are shared, give their energy to 3 vertices. So, and then we have 1 minus 1/2 minus degree over 2 plus degree over 3 is degree over 6. So this is the old curvature which you have. And this can be generalized to arbitrary simplicity complexes by just counting, right? You count how many k-dimensional parts are shared with a vertex, and that can be expressed in the number of, k minus 1 dimensional parts in the unit sphere. But what we do here is we shove everything not to the zero-dimensional part, we shove it to the one-dimensional part. So what happens with a zero-dimensional energy, the zero-dimensional energy doesn't stay, this goes to the edges, but it distributes just to the degree of the vertex many edges. And then we have at the edge, we have a second point. This is the energy of the other vertex, which is again shared with among all these dB vertices, then that's the energy of itself, of the edge itself, negative, right? Because it's odd dimensional, all the higher dimensional parts. But in this case, what we have to look at, it's not 1 over n plus 1 like here, but 1 over the binomial n over 2. Because we just look how many edges are there in a k-dimensional simplex. So that's shared, right? So that's the formula. So you can implement that. For a 2D manifold, it actually simplifies quite nicely. Then you have 1 over the degree of A plus the 1 over the degree of B minus 1/3. So that works, for example, for the icosahedron, right? So we have a 1/5 plus 1/5 minus 1/3. So the curvature in this case at every edge is 1 over 15. That when we have 30 edges, right? 30 over 15 is 2. So we have the Euler characteristic 2. But just here in the case of an octahedron, what we have is 1/4 plus 1/4 minus 1/3 is 2, is 1/2 minus 1/3 is 1/6. That adds up to, then we have, in this case, we have 12 edges, and so we have 12 over 6, we have 2. It also works for one-dimensional graphs. So in one-dimensional graphs, it's 1 over dA plus 1 over dB minus 1. For example, here we have it has to be 0 because it adds up to 0. Here the curvature is at these edges it's 1/2. Also by symmetry you could see that. There is a little caveat here. When we do that whole thing, we just move everything to the one-dimensional part, then we lose the zero-dimensional energies. For example, if there would be another vertex alone here, then that energy would not be counted. We don't, share it in any edge. So by design, this has to have no zero-dimensional part. And then analog, what you can do in the phase case, we just push all the energies not to the vertices or the edges, but we push all the energies to the faces. So that's kind of here. So what we do is we have to look at the degree D0A. That tells us how many triangles are there in which hit the vertex A. How many? So these are the number of edges. So these are the number of triangles which contain AB. So this can be counted, and then that's the contribution of the triangle, which is positive because it's even dimensional. And then this is analog here. We just look for a k-dimensional simplex, how many triangles there are, right? Rx, dimension x plus 1 over 3. That's the number of triangles which there are in a k-dimensional simplex, in a Rx dimensional simplex. R is the dimension. So, and again, one can look just what happens in a two-dimensional case. That's the, case analog here to this Eberhard case. That's 1 over the degree of A plus 1 over the degree of B plus 1 over the degree of C for a triangle minus 1/2. So in this case, in the octahedron here, there are 3/4, because there are 4 degrees, there are 4 triangles at every vertex. So 3/4 minus 1/2 is 1/4, and there are 8 faces, right? You have 8 faces if then the total energy, Euler characteristic, is equal to 2. Another case, kind of if you have a flat situation, right? In a flat situation, all the curvatures are 0. So this curvature is 0, this curvature is 0, all the curvatures are 0. But here the curvature is attached to the face. It's 1/6 plus 1/6 plus 1/6 minus 1/2, which is equal to 0. And that's the icosahedron here. In this case, we have just 1/5 plus 1/5 plus 1/5 because there are 5 faces, 5 two-dimensional faces at every vertex, and then minus 1/2, that's 1/10, and we have 20, that's icosahedron, we have 20 faces, so we have, again, 2. So, I might talk a little bit more next time about curvature when you are deforming it, for example, using wave dynamics, and so that's kind of, then the curvatures change. But the Euler characteristic doesn't change, so it's kind of a cool, really cool framework. That's it for today.